Hello ladies and gents, this is Daniel for Rock the JVM, and in this video I'm going to discuss a very sought after topic in the Scala world, which is Tagless Final, at least for mortals. So this is a video on Scala about the Tagless Final pattern. So this will assume your familiarity with the Scala language. I'm going to write Scala 3 in this video, but this works very well on Scala 2 as well. And as a bonus, you may or may not have read about Tagless Final previously in some article or blog or video or book, or may have already experienced Tagless Final in your own programming experience, but you may be still confused about what Tagless Final actually involves. So, recommendations as always, just write code with me, and whenever you need to refresh your memory about this very interesting concept, just refer back to this video or to the written form at the blog with the link in the description. Now, this particular video deserves special thanks to the original Tagless Final paper written by Oleg Kiselyov and others, who formalized the original Tagless Final design pattern, and also special credits to pretty much every article, book, and video that I could get my hands on the interwebs. This video is a summarization of pretty much everything that I could get my hands on, because no article or video or book was complete enough for my own understanding. So if you're an article or book author and you find something in this video that resembles your stuff, then yes, I've probably read your stuff, and I wanted to combine everything that I could get my hands on in something that I hope to be as digestible as possible for Scala programming mortals, such as myself. So without further ado, let me get back to my little dev environment where I created an object with a main method in case we need to test something. And a word of warning, Tagless Final might not be what you're expecting, and I'm going to tell you why throughout the rest of this video. Now, I wanted to start with a blank slate from the original problem that Tagless Final wanted to solve, which is the expression problem. Now, why do we have this expression problem? We have it because in functional Scala, we think about programs as one giant expression returning a value. And that value can be highly complex, such as an HTTP server or a database or whatever service you might want to spin up, but it's still a single expression. And this is what I teach in both my courses on my website about Scala and functional programming. We want to think in terms of expressions instead of instructions. Therefore, we have this expression problem, which means evaluating an expression while maintaining type safety and returning the right value of the right type. And I'm going to start with a very simple example. So I'm going to call this little object, I'm going to call this expression problem. And here, assuming I can type, I'm going to define a trait. I'm going to call this expression, or expr for short, and I'm going to define some case classes denoting booleans. So this expression can be thought of as one giant boolean expression based out of boolean operators and operands that can be evaluated to a single value. And I'm going to define a case class. I'm going to call this b for simple value, and I'm going to have a boolean as a boolean which extends expr, and I'm going to have a case class for operators. For example, OR, which has a left operand as an expr and a right operand as an expr as well, and this extends expr2. And then I'm going to define a case class called AND, which has a left as an expr and right as an expr, and this extends expr. And another case class, let's say NOT, which has an expr and this negates it. So I'm going to have expr here. So we have a bunch of operators, all of which are boolean, and some operands, or, and not. One such expression would be something like a giant boolean as an expr, and I'm going to have, for instance, an or between an and with boolean true and another boolean false. And here, as the second operand of OR, I'm going to have a boolean of false, for instance. So this is one expression that can be evaluated to a single boolean if we traverse that as a tree. All right, so this is the kind of stuff that we want to solve. We want to evaluate this expression to a single value. So I'm going to define a method called eval, which takes an expr as an argument, and this returns a final boolean that I can use. And as an implementation, all we have to do is run a pattern match. So I'm going to have expr match, I'm going to have a Boolean with a B, then I'm going to return that B which is wrapped inside. In case I have an OR with, let's say, two expressions A and B, I'm going to have eval for A or eval for B. So recursively, and similarly for the other stuff, so I'm going to have an AND for A and B, and I'm going to return an eval for A and eval for B, and in case I have a not with an expression, I'm going to return not, so not eval for that particular expression. So notice that I'm recursively evaluating the nested expressions inside, but finally, at the very end, I'm always going to return a Boolean. Now, all of this is pretty easy until we try to add new stuff to our little program over here, because we have expressions only of type Boolean. But if we want to define a bigger set of functionalities, for instance, if we want to process numbers as well, and also subject that to the same eval function, we'll get into trouble. So if we want to, for instance, include ints, I would have a case class, let's call this I for an int, and this extends expr, and a case class to, for example, process numbers. I'm going to call this sum for left, which is an expr, and right, which is an expr, and this extends expr. Now, if we wanted to include I and sum here in my eval function, I'm going to run into trouble because if I want to process integers, I won't be able to return booleans at the very end. I should be able to return either boolean or int, depending on the type of expression that I find. And so I would have to define another method. I'm going to call this eval version 2, which takes an expression as an argument, and this returns either a Boolean or an int if you're happy to work in Scala 3, or if you're doing Scala 2, you'll need to return a general type any, which lost type safety. So all I can do now is to run that same pattern match. So I'm going to run my expr here, but if I do my pattern match, my eval A and eval B are not known to be Booleans, so I would have to do casts. So I'm going to have as instance of Boolean, eval B as instance of Boolean, and so on and so on. So you would have to write casts everywhere. Not to mention that some evals may actually be instances of I or sum, which are not Boolean. So the loss of type safety can actually mean the crash at runtime, which is something that we don't want. So the expression problem means, how do we structure our data types such that we can submit an expression of type Boolean and return a Boolean, and submit an expression of type integer and return a proper integer through the same evaluation function? This is the expression problem. And this might sound a little contrived, but if you think about it, because we're writing pure functional Scala, all of our programs are of this style. All of our programs are giant expressions returning a value, and we want to return the right type for the right expression that we are using. So this problem is very relevant and very, very general. So I'm going to move forward and try to solve this example, which I'm pretty sure you understand, and then we can generalize that to other things which might be closer to real life. Now, I'm going to call this object, I'm going to call this solution1, and I'm also going to name it after we solve this expression problem in the first solution. Now, in order to differentiate between integers and booleans, one solution would be to add some external information to this trait. For example, we might want to add a small tag which denotes whether this expression is of the type Boolean or if it's of the type int. So I'm going to define a trait. I'm going to call this expr, and I'm going to have a val called tag, which is a string. Now, in Scala 3, we can pass constructor arguments to traits. If you don't want to, or if you're using Scala 2, you can define this val tag inside the trait. All right. Now I'm going to define a case class. I'm actually going to define case classes for all the data structures that we're using here. So I'm going to copy and paste all of them. So I'm going to have case class B, which is a Boolean and extends expr of type Boolean. And I'm going to use this tag over here to all the Boolean expressions. And I'm also going to copy the integer types, and I'm going to pass the argument type, let's say int, here. So notice that I've added some extra information to the expressions so that we can differentiate between Boolean and integer types. Now, if we want to write the eval function, which takes an expr as an argument, this will still have to return the any type, because we need to return a Boolean if this is a Boolean expression and int if this is an int expression. So the final return type should still be any. And I will have to run a pattern match yet again. So I'm going to have expr match. Now, the advantage here is that now we can implement the proper cases and differentiate between the tags, because we can tell from these strings which expressions are valid and which are not. So for instance, I can say case B of type Boolean, and I'm going to return that particular value. And in case I get an OR for left and right, now I can validate if left and right are of the right Boolean type. So I can say if left.tag is not equal to bool, or right.tag is not equal to bool, then I can signal an error. Maybe I can throw new, let's say, legal argument exception, let's say improper argument type, or something like that. Otherwise, I'm going to return the right evaluations, so I can do the proper casts. So I can then say eval of left, and I'm going to say as instance of Boolean, because now I'm safe, or eval of right as instance of Boolean. So my typecasts are now safe because I've checked against the tags, and so on for all the other expressions. Now notice that this solution, although it does return the right type for or the right value for the right expression type, is still type unsafe for the type any, and it still crashes with a different kind of exception if the tags are of the improper type. So in effect, we haven't solved that much. We can surface the illegal argument exceptions at the very beginning of the construction of the expressions, which might be a little better. So I can say assert. So I'm going to say assert that left tag is equal to bool and right tag is equal to bool. So I'm going to copy this, and I'm going to use the right operators. So I'm going to have left tag must be equal to bool and right tag must be equal to bool. And if this condition holds true, then I don't need to run these extra checks, and I can do my casts without any other concerns. However, the illegal argument exceptions, or the assertion failures, still happen at runtime. So in effect, the solution 1 only adds some extra let's say peace of mind when we actually end up evaluating, but functionally we haven't solved that much. This solution 1 is called tagging, because we're adding this tag which we use to differentiate between the different expression types. So this solution moves at least a little step in the right direction, because the expressions are validated for correctness at construction with these asserts instead of at evaluation phase. However, we still don't have any type safety, and the errors are shown at runtime. So maybe, just maybe, we can do a little better. So I'm going to show you a solution number 2. Now, because Scala is a strongly typed language and it has generics, maybe we can use the generic type argument as the tag for differentiation between expressions. So here's what I'm going to write. I'm going to write a trait. I'm going to call this expr, but I'm going to add the tag in the form of a type argument. So this eliminated the string tag. So I'm going to call this expr a, and I'm going to add the case classes for Boolean, or, and not, and I'm going to add the right type. So expression of type Boolean, and I'm going to use the Boolean type everywhere. So I'm going to use this thing, and as well on the argument expr Boolean. And for the int types, so for the int expressions I and sum, I'm going to add the generic type argument for expr of type int. And the int type argument needs to be present here on the I and sum respectively. So notice that we've eliminated the tags, but we now have the type arguments. And the eval function now needs to take a type argument a and an expression of type a, and this will return the right type for the right expression. And the implementation is going to be expr match, and we're going to run the pattern match for all the appropriate types. So in case we get a b of type boolean, then I'm going to return that. In case we get an I of type int, I'm going to return that. If I have a case for or with left and right, I can safely do eval of left or eval of right, because left and right are known to be expressions of type boolean by definition, and also for the int type. So I'm going to have an sum with left and right, and I'm going to have an eval of left plus eval of right, and so on. So notice that we are returning the right type for the right expression without needing tags. And this solution number 2, I'm going to call tagless. So this is a tagless solution to the expression problem, because we can now return the appropriate type for the right expression, and the expressions are differentiated by their generic type arguments without runtime tags. So I'm going to show you how this would work. So if I have outside the tagless thing, I'm going to have a method called demo tagless, and I'm going to have no arguments, just like that. I'm going to import tagless so that I can import the types and the function, and I can print line, for instance, eval for or with boolean true and with boolean true and boolean false. This is a proper expression, and it's proven to be correct or not at compile time. So if you pass the wrong types, then the function will not work. So if I try running this sort of operation with boolean with 43, for instance, then I'm going to get a compiler error because 43 is not of the appropriate type. So notice that in this case, the correctness is proven at compile time by the compiler doing the type checking for all the appropriate types in the data structures. And similarly for int, so I can say print line with eval with sum with int 24 and int with -3 or something like that. And if I call demo tagless, we are going to see the right values here. All right, so we have the value true for the first expression and the value 21 for the last expression. So this is the tagless solution to the expression problem. Now, this is not the tagless final solution to the expression problem, because instead of the final value that we're working with, which is the booleans or ints that we're ending up with after evaluation, we're working with intermediate data structures such as the case classes that we're using here, which is why this solution is called tagless initial. Now, if you want to work with the final ints or booleans at the end of evaluation, you're going to end up with what is called tagless final. And I'm going to define a trait called expr a as before. So it's tagless because we have the generic type arguments to make the difference between boolean expressions and int expressions. And here inside this expr a, I'm going to have a value which is of type A, and this is the final value we care about after evaluation. Now, the difference is that in this situation, creating instances of these expressions will be done a little differently. And in this case, I'm going to define methods that will resemble our case classes. So I'm going to define a method called b for a boolean, and this is going to return an expr of boolean. And this is going to be a new, assuming I can type in the right place, new expr of boolean, where the value is that particular boolean that I'm just receiving as an argument. And same for the other things. So I'm going to copy and use a def. I'm going to call this I, where the argument is an int, and this is of type int, and the expression is going to be an expr of int all over. And just for the sake of argument, I'm going to define two more. I'm going to define an or, where the left is an expr of Boolean, the right is an expr of Boolean, and finally we're going to get a new expr of Boolean where the value, so the val value, is going to be left.value plus right.value. So notice that the evaluation, not plus, but or, in this case, the value is computed right at the construction phase. So the evaluation happens instantly. And same for the sum. So if I have a sum for left, an expr of int, and right as an expr of int, this is going to be a new expr of int where the val value is going to be left value plus right value. So we have Boolean, ints, and two operators for Booleans and ints. Obviously, you can implement the rest. Now, in terms of evaluation, we're going to have a method called eval, which takes a type argument a, and an expr, which is an expr of a, and this is going to return an a as expr.value because the expr trait has this member called value. So notice that the evaluation happens pretty much instantly. Eval is just a wrapper over the value that the expression already has. So in this case, the evaluation happens in each of these methods independently. And this is the difference between this solution and the initial tagless solution, because in this case, we're working with the actual values that we care about, which is the result of evaluation. And here I'm going to define a method called demo final tagless, which is going to return unit. I'm going to import tagless final, and I'm going to print line pretty much the same thing, except in this case I'm not going to use the or and sum with the caps. I'm going to use the or b lower caps a lower cap b, lower caps b, and the sum, which is lower caps a, I, and I. Now, I don't have an and. I might just create one really quickly. I'm going to define a method called and here, and the implementation is going to be left value and right value, and we have a final tagless ready to demonstrate. So in main, I'm going to run this, and we're going to see the same result as before. So we're going to see the true and 21, noting that the final tagless method also works correctly. So this is a variant of the tagless design pattern where we work with the actual evaluation directly in the expression. And at the very end, all we have to do is just surface that value out. This is the tagless final pattern. That is it. And the question that I might get at this point is, where's the F in the tagless final pattern? Usually, when we look at tagless final in articles or books in Scala, we often refer to this sort of stuff with the higher kind of type F, for which there is an implicit type class of your choice, example monad, as quote-unquote tagless final. And the question is, how is this related to tagless final? Now, tagless final and type classes are two completely separate concepts. Tagless final is a design pattern, I want you to think of it that way, that solves a particular kind of problem, which in this case is the expression problem, and all we have to do is program against an interface, and the implementations of the interface define the logic of our program. So tagless final is nothing rocket science, it's just programming to interfaces for a particular kind of problem. I want you to think of that as a simple design pattern. Whereas type classes are a set of functionalities that you want to offer for some types and not for others. Tagless final is a solution where you want to return the right type for the right expressions and not for other types. So notice that there is an overlap in representation between type classes and the kind of problem that tagless final wants to solve. And there is a variant of tagless final that can use higher kind of types. And I'm going to sketch one here. I'm going to call this tagless final version 2. where the creation, or rather the logic of the expressions, creating a Boolean expression, all these operators, are grouped together under a simple type class. I'm going to define that as my type class. And I'm going to define that in terms of a higher kind of type E for expression. And the type class will contain all of these operators, and the type class has the capability of creating expressions of that type. So for instance, I can create a method called b, which wraps a Boolean, and this returns an E of Boolean, regardless of what kind of type E is. And I'm going to define a method called I for an int as an int, and this will return an E of int, and so on. So I'm going to define, let's say, or with left as an E of Boolean, and right as an E of Boolean, and this returns another E of Boolean, and I'm going to copy that shamelessly, and I'm going to paste that in an AND method. And finally, I'm going to define a sum, which has a left as an E of int, and right as an E of int, and finally, I'm going to return an E of int. So notice that all of this is very abstract, and all these functionalities were grouped together under the type class. This has a fancy term, and it's called an algebra. This is too fancy a term for my liking, but just to separate ourselves from the type class name, I'm just going to name this algebra. Now, an implementation of the algebra will have as a generic type argument a concrete representation of an expression. So I'm going to define my little case class. I'm going to call this exper, and this has a type argument a containing a value of type a, just like that. And I'm going to define an algebra of this kind of expression. And I'm going to call this simple expression, because it's very simple, it just wraps a value. Now, I would like to implement an instance of algebra that is applicable to this simple expert type. So I'm going to define that as a value. I'm going to call this simple algebra. And actually, I'm going to define that as a given instance, because it's the only one that makes sense for this simple expert. So I'm going to have simple algebra as algebra of type simple expert with, notice I'm using the Scala 3 syntax here. You can define an implicit val with the exact same significance. And I'm going to define my methods. So the Boolean is just going to return simple expert with that Boolean. And I'm going to override the I method, which wraps a simple expression over an int. I'm going to override the OR method that takes two simple expressions of Boolean. I'm going to return another simple expression, which wraps left.value or right.value. So notice that the evaluation also happens here at construction phase, which is very similar to the pattern that we wrote before. And I'm going to copy that shamelessly. I'm going to name that and finally, I'm going to implement it in the right way. So left value and right value, and I'm going to finally override sum, which takes two expressions of type int, and I'm going to return another simple expression of type int with left value plus right value. So notice that at this point, it's just a matter of organizing code. Now, in order to actually run programs in the style of this kind of expressions, we will need to use this type simple expr with the simple algebra as its given value. So I'm going to define, let's call this program1, which is the representation of OR between a true and an AND between a true and a false. So I'm going to have program1, which takes a type argument e, which is the expression type, and I'm going to have a using clause, which in Scala 2 would be an implicit argument. I'm going to call this alg for algebra. So algebra e, and this is going to be an e of Boolean. And I'm going to say, for instance, import alg.everything so that I don't have to write all these methods prefixing alg all the time. And I can actually shamelessly copy this entire program, and I'm going to return this same structure. So this actual expression, which wraps true, true, false, and all these methods on the alg thing that I pass as a given value. Now, if we want to realize a concrete instantiation of this program and evaluate it at runtime, we are going to demonstrate that. I'm going to also run the program2. So def program2. Let me copy this signature. I'm going to call this program number 2, which is the something, which I wrote after that. So this is an e of int. And finally, I'm also going to have an import with alg everything. And I'm going to take this exact expression, copy it, and return it in the method for program 2. And finally, if I want to print these to the console, so I'm going to have demo final tagless version 2, I will need to import tagless final version 2 everything. And I'm going to have a print line of, and I'm going to use program 1 with the type simple expr, and print line program 2 with the type simple expr. This is pretty much what happens in programs written with cat's effect, because at the very end we instantiate that with the proper effect type IO in that case. So let me print this in main, run this application, and we're going to see the exact same values, simple expr with true and simple expr 21. Also, I can obtain the final value at the end if you're interested in that. All right, so true and 21. So notice that we obtain the final results regardless. And this Tagless Final version 2 is much closer to what you've probably seen in programs that style themselves to using Tagless Final. But this is not a requirement for Tagless Final. Tagless Final was completely solved in the previous solution where we built expressions with the evaluation right at construction phase. This is just a reorganization and a further abstraction down the line. So we basically refactor the code to use a type class instead of a plain interface, but the concept remains the same. And the concept of Tagless Final and the concept of type classes are completely separate, orthogonal, some might say, but they have an overlap in how the code ends up looking like when you apply the Tagless Final pattern in the style that I've showed you here. But other than that, Tagless Final and type classes have nothing to do with each other. Now the question is, how might we use something like this? How do we go from an example that looks kind of contrived with Boolean expressions and integer expressions to something more real life, like a server or something like that? Well, this algebra might be refactored to, say, for instance, a user login. And this user login trait can be thought of as an abstraction of the kind of actions that might be done when a user logs in. So for instance, I can check whether a user has logged in using multi-factor authentication. So I can say check login. And the Boolean here can be MFA, so multi-factor authentication. The I can be refactored to a different name, for example, last error status, which is an int. I'm going to call this a code. I'm going to refactor that. The OR can be thought of, let's say, multi-factor authentication or something like that. Multi-factor authentication version 1. So MFA version 1. Left and right can be factor 1, or let's say email and password. And the second argument can be SMS. All right. And the AND can be multi-factor authentication version 2. Left can be phone. And in this case, we need, for instance, I don't know, a mobile app. And the sum can be refactored to, let's say, total session logins from server 1 logins and server 2 logins. Cool. So this user login is our little authentication capability. The simple expression can be user login status, and simple algebra can be implementation. So login flow or login capability implementation. So notice that from a Boolean kind of problem, we very quickly got into real life. So this user login is a set of capabilities that we want to offer, and similarly for all kinds of services that we might want to provide. And program 1 can be, for instance, user login flow, and program 2 can be check last status. Okay, and in this case, our code becomes very similar to what a real-life implementation of a service might look like, of course, in a simplified version. But notice that Tagless Final can be very, very applicable to real services. So I hope I managed to give a quick and digestible overview of Tagless Final in Scala. If you got to this point thinking that TF is just a fancy terminology for programming to interfaces, then you got the point and I've done my job. I hope you liked this video, in which case I recommend that you subscribe to the channel for more videos like this. Check me out on Twitter and LinkedIn for fresh updates on upcoming material, and check out my website at rockthejvm.com for lots and lots of content on Scala and functional programming, Akka, Cats, Cats Effect, Apache Spark, and so much more. Until next time, I'm Daniel, signing off.